Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to my channel. I'm Asif Math Corner. Today we will learn about idempotent element in group theory. What is idempotent element in group theory? Let's start the lecture. Idempotent element. An element X of a group G is called idempotent if X steric X is equal to X itself. When we operate by a binary operator steric two elements and give the result is itself element, then it is called idempotent. For example, when we multiply identity element to identity element, it gives us identity element. Multiplicative identity is 1. When we multiply 1 by 1, it gives us 1. Like that, additive identity is 0. When we 0 plus 0, we get 0. So, when the operator is addition, we can talk about the additive identity, and when the operator is multiplication, we may say that it is the multiplicative identity. 1 multiplied by 1 is equal to 1. So, let's take a theorem related to this idempotent element. So, the theorem is the only idempotent element in a group G is identity element. He said that only identity element is idempotent element. No other element can be idempotent. Let's come to the proof. Let X belongs to G be an idempotent element, then by definition, as we read before, X steric X is equal to X. If the steric is multiplication, then X square is equal to X. This implies that X square means X dot X is equal to X. Very easy to understand till here. Next, as we know that G is a group, so if X belongs to G, then we know that X inverse also is equal to G, because every group, in group, every element should exist its inverse. So, multiply by X inverse both sides. So, we have read that X dot X is equal to X. When we multiply by X inverse both sides, so X inverse dot X and X inverse dot X, we know that when an element multiply by its inverse, it gives us identity element. So, X inverse X is equal to E, and here X inverse X is equal to E. And when identity element multiply by any element, it gives us the same element. For example, 1 multiplied by 2, it gives us 2, and 1 multiplied by 3, it gives us 3. So X multiplied by identity then give us identity. So X is equal to E. So the element is identity element, hence proved. Let's come to another theorem, the very important theorem. In a group, if every non-identity element is of order 2, then prove that the group is abelian. As we read before that in my previous lectures, cline 4 is E, A, B and C. The cline 4 has 4 elements, and every non-identity element we have read that A square is equal to identity, B square is equal to identity, C square is equal to identity, and we prove that also by a Euler table that the cline 4 is an abelian group. Here we take a general example. Let's come to the proof. Let G be a group and A belongs to G, and A is not equal to identity element. such that a square is equal to identity. Because we said that in the theorem definition, element of order 2. Order 2 means it's the power of 2 give us identity. Every element those has order 2, it's mean that the power of that element 2 give us identity element. So a square is equal to e, which means that a square means a dot a if the operator is multiplication is equal to e from this definition. This implies that when we multiply inverse on both sides, a inverse on both sides, so a inverse a, as we read in the previous theorem, a inverse a is equal to identity element, and a inverse into identity any element or inverse of any element when multiplied by identity, it gives us that element. So a inverse, when the element multiplied by identity give us same element, a is equal to a inverse. By this result, by taking this result, we can easily prove that the element those have order 2 make an abelian group. So let x and y belongs to G, and as we talk about previous that every element is its self inverse. A is equal to A inverse, B is equal to B inverse, X is equal to X inverse, Y is equal to Y inverse, and X into Y is equal to X into Y inverse. As we know the property of inverse, it's change the order. So Y comes first, Y inverse is equal to X inverse, and we know that Y inverse is equal to Y and X inverse is equal to X. Hence, this and this xy is equal to yx, which is we know that commutative property hold. Commutative property hold means that it is an abelian group. Here the proofs end. So I hope you understood, and please share this video because your share has a value for that student who need it, whose problem may be solved by this video. So share it and subscribe my channel if you like it. Allah Hafiz.